All right, let's dive in. Today, we're going to build a bridge from that invisible world of ones and zeros, the language of machines, to the numbers we see every single day. We're going to demystify how a computer's code gets translated into something we can actually read. You know, it seems almost like magic, doesn't it? A number just appears. But behind that glowing 8 on your alarm clock, there's this really cool process of translation happening. A machine is speaking its native language, binary, and a tiny little circuit is acting as an interpreter, turning it into a shape our brains get in an instant. Today, we're going to pull back that curtain. So to really get how this works, we need to meet the two key players in our story. I want you to think of them as a team. One does all the thinking, and the other, well, it does all the showing. We've got the brain, which handles the logic, and we've got the face, which gives us that final visual result. And here they are. On the left, we've got our brain, the IC7447. It's a BCD to 7-segment decoder. Now, BCD just stands for binary coded decimal. It's just a super simple way for machines to count from 0 to 9. So this chip's whole job is to translate that code. And on the right, that's our face, the 7-segment display that's going to show us the final number. Let's zoom in on the brain for a sec. The IC7447 is this specialized little chip. Its entire purpose in life is to listen for that 4-bit BCD signal, and based on whatever code it hears, it knows exactly which of its output pins to turn on to create a number. It's the crucial translator in our whole operation. And here's our face. You know, the 7-segment display is actually brilliantly simple. It's just 7 little light-emitting diodes, LEDs, arranged in a figure 8 so they can form any digit. The kind we're using is called common anode. Now that might sound technical, but all it means is that the positive side of all 7 LEDs are tied together and hooked up to power. So to light one up, the IC just has to connect its negative side to ground. That's it, circuit complete. Okay, so we've met the team. Now for the big question, how do we get them to talk to each other? Well, the answer is in the pinouts. This is our blueprint, our instruction manual that tells us precisely where every single wire needs to go to make this thing work. Think of this chart as our map for the IC7447. It's pretty straightforward. Pin 16, that gets our 5-volt power. We call that BCC. Pin 8 goes to ground. Simple enough. Now, the really important ones for us are pins 7, 1, 2, and 6. These are our 4 inputs where we'll send our binary code. And finally, pins 9 through 15 are the outputs that connect right to the 7 segments on our display, telling them when it's their turn to shine. And the display's map, well, it's even simpler, believe it or not. For this common anode type, those center pins get hooked up to power, and the outer pins, they match up directly with the segments, A through G. All we got to do is connect the dots from the IC's outputs to these inputs. Okay, enough talk. Theory's over. It's time to take this blueprint and actually bring this circuit to life on the breadboard. We're just going to follow a few simple steps to get everything connected and ready to go. Let's do it. First things first, every circuit needs some juice. So we're going to connect pin 16 on our IC to the positive 5-volt rail on the breadboard, and pin 8 right to ground. Then we'll do the same for the display. Connect its center pins to that positive rail, but we'll run it through a resistor first, just to limit the current and keep those LEDs safe. Now for the most critical part, we've got to connect the brain to the face. This is like hooking up all the nerves that are going to make this thing work. We're going to take a wire from each output pin on the IC and connect it to its matching segment on the display. So pin 13 goes to segment A, 12 goes to B, and we just keep going until all 7 are wired up and ready for their signals. Last but not least, we need a way to actually talk to the brain. So we connect 4 wires to those BCD input pins, A, B, C, and D. By connecting these wires to either power for a 1 or to ground for a 0, we can send any 4-bit number we want to our little decoder chip. All right, this is it, the moment of truth. The circuit is built. It's time to power this thing on and see if our little translator actually works. We're going to feed it some binary codes and see what numbers pop up on the display. Let's have some fun. So let's start with the easiest one out there, the number 0. In binary, that's just 0000. To do that, we connect all 4 of our input wires, A, B, C, and D, straight to ground. That sends a low or 0 signal for each one. And look at that. It works. With an input of 0000, the IC decodes it, lights up every segment except that middle one, and gives us a perfect, beautiful 0 on the display. Awesome. Okay, 0 was easy. Let's try something a little different. How about the number 3? Well, the binary code for 3 is 0011. So this time we set inputs A and B to high by connecting them to power, while C and D stay low connected to ground. And bam! Just like that, the display changes. The IC reads that 0011, it knows that means 3, and it switches on the exact right segments. This thing is definitely working. All right, let's go for broke. Let's jump all the way to our highest single digit, the number 9. The binary for 9 is 1001. So we set input D, which represents the number 8, to high, and input A, which represents 1, to high. 8 plus 1, that equals 9. See? That's how the chip thinks. And there it is. Perfect. The decoder gets that 1001 signal and instantly lights up the segments to show a 9. We've successfully taken our circuit for a test drive, from 0 all the way to 9. So let's just step back for a second and look at the big picture here. What we've built is, it's more than just a number display. It's a perfect working example of a really fundamental concept in all of digital electronics. So let's just run through that one more time from start to finish. We start by giving it a simple 4-bit binary input. The IC7447, our amazing translator, does all the heavy lifting of figuring out what that code means. It then grounds the right combination of output pins, which closes the circuit for specific LEDs on the display, and they light up in a pattern that we instantly recognize as a number. We've turned machine speak into plain English. And that's really the magic of it, isn't it? This incredibly simple circuit is a perfect model of a digital-to-visual interface. It's one of those foundational building blocks that allows all the complex digital systems out there, from massive supercomputers down to your microwave, to communicate with us in a way we can immediately understand. What we've really seen today is how one tiny logic chip can act as a translator between two different worlds. Now, just imagine what happens when you combine thousands or even millions of these simple ideas. Every complex digital device you own is built on this very same fundamental concept. It all starts right here. So the real question isn't just how it works, it's what are you going to build with it? Thanks for joining me.